Hello. On the second half of this lecture, we're going to talk about the momentum wave vector relationship. We're going to define the effective mass of the electron, and we're also going to start with the definition of the carrier density and the carrier concentration. So in order to do this, let's recap a few of the concepts that we've seen previously. What's the wave vector k? Okay, initially we saw the wave vector k as part of the wave function. So the direction of the wave vector k corresponds to the direction of the propagation of the wave function psi. The wave function is associated with the probability of finding the electron. We saw that if you take the absolute value of psi and square it, you have the probability density function. And so it's the function that defines the probability of finding the electron inside the semiconductor. And inside a periodic lattice, we saw that this function would behave in this way. It would be the product of a periodic function of position r for a given k, for a given wave vector, and this term, which is, as we saw, a plane wave propagating in direction k in the three-dimensional space. So this term corresponds to a plane wave. But aside from being the wave vector, k is also related to the momentum, as we'll see. So through the wave vector k, it's possible to define the quasi-momentum or the crystal momentum p, okay, in such a way that the momentum p has a linear relationship with the wave vector k. P is equal to h bar, the modified Planck constant, multiplied by the wave vector k. This is the linear relationship between p and k. So you see that there's a direct proportionality between p and k. Okay, if we recall that in classical mechanics, the momentum of a particle p is equal to the mass times the velocity of the particle. This is the analog to momentum when we're talking about electrons moving inside the crystal lattice. Therefore, the direction of motion of the electron inside the solid points in the same direction as the k vector. These two vectors will be pointing at the same direction since h bar is simply a constant. Also recall that when we were talking about indirect bandgap semiconductors, so we had band structure like this, and in order for there to be emission, we needed for the electron to make a downward transition from the conduction band into the valence band, and it would need to undergo a change in wave vector k of exactly the wave vector mismatch delta k, besides undergoing a change in energy. Well, this means that since k is directly proportional to the momentum p, or the crystal momentum p, that this implies a change in momentum as well. So this is why we said that, in indirect bandgap semiconductors, aside from undergoing a changing energy, the electron also needs to undergo a changing momentum as well. Okay, and this is less likely to happen, and that's why these materials were not good emitters of electromagnetic radiation. So inside a semiconductor or a crystal lattice, the electrons are going to be affected by the electrostatic forces of the nuclei and other electrons inside the material. So you can consider the material as a periodic arrangement of atoms, and these atoms, since they're made up of positive and negative particles such as protons and electrons, they're gonna subject the electron to a periodic potential as well. In fact, we call this V of R. And therefore, if the electron is moving inside this material, let's say that this is the electron, it's going to be subjected to these electrostatic, periodic electrostatic potential as well. So it's going to have internal forces, and by internal I mean forces that are associated with this periodic potential inside the material. So the forces arising due to the periodic lattice of atoms. Okay. On the other hand, if you take this material and you apply to a piece of semiconductor or material an external field, the electron is going to be affected by this external field as well as the internal field. So the total force exerted on the electron is going to be F total equals to F external plus F internal. Again, F internal is the force due to the periodic potential, and F external you could obtain it if, for example, you placed this material inside a capacitor or parallel plate capacitor and applied a voltage source across it. So you would get an electric field in this direction, right? So this would be responsible for the external force. Since the electron is a negative charge, it would move opposite to the external electric field. So the external force is due to the applied electric field only, which we're calling E external here. Okay, so E here does not stand for energy, it stands for electric field, and it obeys, the classical electrostatic law. So since it's a negative charge, the force, the external force on the electron is going to be minus the charge of the electron times the electric field. The internal force is due to the internal electrostatic field, which is periodic. Okay, so the point is that if we define the crystal momentum P as being h bar times the wave vector k, it is as if the electron were responding only to the external field. So we can treat this momentum as the momentum that the electron would have if only the externally applied electric field were acting on the electron itself. Okay, so this is very useful because we can, by using this, it can be shown that we can disregard the internal electric field due to the periodic arrangement of atoms and treat the electron as if it were a free particle moving inside the solid with exactly this momentum. So beside the crystal momentum, it's also useful to define the effective mass of the electron, m star. Okay, so it is defined in such a way that m star is the inverse of 1 over h bar squared times the second order derivative of energy with respect to wave vector k, okay, the absolute value. So we notice immediately that this term here can be obtained from the band structure. So if we take the red curve here, for the conduction band CB and the valence band VB, by taking the second order derivative of E with respect to K, we could calculate the effective mass. And we notice, if we compare the red curves with the green curves, that, well, let's see, the second order derivative is the derivative of the first order derivative. So the rate of change of the first order derivative of the green curve, we can see that it's much faster than the rate of change of the first order derivative of red curve. So therefore, the second order derivative of the green curve is larger. Well, the effective mass is proportional to the inverse of this, and therefore, since the second order derivative is larger for the green curve, the mass is going to be smaller. So the electrons, corresponding to this conduction band in green would have a smaller mass and would therefore be lighter and move faster through the lattice if subjected to an electric field. Okay, so this kind of information can be obtained from the band structure as well. Okay, so m star is the apparent mass that the electron has when an external field is applied, so that Newton's second law is obeyed if you replace the mass by m star. In other words, F external is the rate of change of the momentum with respect to time, the derivative of momentum with respect to time, which is equal to, if the mass is constant, m star multiplied by the acceleration. So to summarize, the electron is going to be subjected to both the internal and external forces. The internal one being the forces related to the periodic arrangement of atoms, the attractive forces due to the nuclei and so on. But if the momentum and mass are defined as in 1 and 2, which we've just done, it is as if the electron were responding to the external field only. So it's as if the electron were a free particle inside the solid, and its momentum and mass were respectively obtained by equations 1 and 2. To finish off, let's talk about carrier concentration. So in a semiconductor, only electrons and holes that have enough energy to move to the conduction band, this would be electrons, or holes that move to the valence band, contribute to current conduction. Okay, so this is the picture. At 0K, all of the states of the valence band are going to be filled. As you raise the temperature, or if you dope the materials, you can introduce electrons in the conduction band and also, leave empty states or holes in the valence band. The total carrier concentration, N, in centimeter to the minus third, is defined as the number of electrons per unit volume of solid in the conduction band. Okay, so the carrier concentration N is going to be the number of electrons per centimeter cubed, and therefore if you take a cube of 1 centimeter by 1 centimeter by 1 centimeter on its side, it's going to have N electrons. A related concept is the carrier density, which is defined as the number of carriers, electrons or holes. For electrons we usually use N, for holes P, the number of carriers with energy between E and E plus dE. And usually the carrier density is written as N of E. So the only difference between the carrier concentration N and the carrier density N of E is the fact that you explicitly write the E dependence when you're writing the carrier density. It's a different variable altogether. So by definition, N of E is the number of electrons with energies between E and E plus dE. So if we think about the band structure, let's draw only the conduction band, okay? And let's say that this conduction band is filled with electrons in this manner right here. So these are all electrons at different energy levels in the conduction band. From this definition, N of E at this energy value is the total number of electrons between E and E plus D. So let's say that this is D. Of course, D is infinitesimally small, and all of the electrons in this range would be N of E, the carrier density. Not to be confused with the carrier concentration. Therefore, if you integrate the carrier density over all of the energy values in the conduction band, okay, you will get the carrier concentration. In order to get the carrier concentration, you need to integrate over energy from the band edge. So this would be EC, the band edge of the conduction band, up to infinity, or up to the entire range of the conduction band. Actually, you integrate N of E, or the carrier density, in order to obtain the carrier concentration. So if you sum up all of the electrons in the conduction band, you're going to get the carrier concentration. But the carrier density for energy E is the number of electrons with energies between E and E plus dE. Okay, in such a way that the carrier density can be thought of as the number of electrons per unit energy for a given energy value. In other words, if N is equal to the integral of N of E with respect to energy, we can presume that N of E, the carrier density, is the derivative of the carrier concentration N with respect to energy, right? Okay, absolutely similar definitions can be done for whole carrier concentration, for whole concentration P. Okay, but usually you denote the whole concentration as P and the whole density as P of E, in the same way that N is the electron concentration and N of E is the electron density or electron carrier density. And you can also write that the whole concentration is equal to the integral from minus infinity to the edge of the valence band. So let's call this EV of P of E, the whole density over this range. Now we're going to define two new quantities associated with the carrier concentration. Okay, so let's talk about electrons for a minute here. So the electron carrier concentration can be written as the product of the density of states in the conduction bands rho c of E multiplied by the probability of occupation f of E. This is the Fermi function, probability of occupation, and this is the density of states, and the carrier density is the product of these two. Okay, so the density of states, for the conduction band rho c of E is the number of available states per unit volume of material with energies between E and E plus dE. Okay, so similar to the carrier density, you can define density of states. So let's say we're talking about, the conduction band. You're going to have a certain amount of states per unit energy along the conduction band and the valence band as well. So these are the available states that you have up here that can be occupied by electrons in such a way that rho c of E for energy E is equal to the number of states with energies between E and E plus dE. So differential energy dE, the number of states in this range is rho of E. Right? And it's straightforward to see that the carrier density, the number of electrons that can be within this range, is going to be directly proportional to the density of states. The more states you have here, the more energy values that can be occupied by electrons within this range. So if you have more states, there's a higher chance that you're going to have more electrons within this range. But also, you need to take into consideration the probability of occupation. So there's going to be a function that is going to define the probability that the states within this range are occupied or not. Okay, obviously the function is going to vary between 0 and 1. If it's 0, there's 0 chance of occupation, so there's 0 chance that there's an electron in that state, in that particular state, and if it's 1, it's a 100% chance that there's an electron there. Okay, so that's the f of E. And of course you can see the straightforward direct relation between N of E and f of E. The higher the probability that these states are occupied by electrons, the more electrons are going to be there. Okay, so N of E is proportional to both the density of states and the probability of occupation. So the probability of occupation, F of E, is the probability that the state with energy level E is occupied by an electron, as we've just said. We're going to define explicitly this function in our next lectures. Okay? Of course, completely analogous definitions can be done in the valence band. So in the valence band, you can write that P of E, the whole density, is equal to the density of states in the valence band, which is a function of energy as well, right? You can have, let's say we're talking about the valence band. You can have certain energy values that have less states and other energy values where the energy states are closer together and you have more states. So let's say within this range you have more levels than within this range right here. Therefore, here the density of states is smaller than here if the states are closer together in this region. But going back to the carrier, to the whole density is going to be the density of states in the valence band multiplied by the probability of occupation by holes, which is, as we'll see, 1 minus the probability of occupation by electrons, f of e. Let's do the square brackets here. So you can consider this as the probability of occupation of these states by holes. Okay, if they're not occupied by electrons, they must be empty and they're going to correspond to holes. Therefore, 1 minus the probability of occupation by electrons is the probability that the state is going to be empty, and therefore the probability of occupation by holes. We're going to talk about this in future lectures. Okay, so this was it for today's lecture. On our next lecture, we're going to further develop the concepts of density of states and probability of occupations for holes and electrons. So thanks very much for your attention, and I'll see you around.